This angle could be take any value between 0 to 2 pi, depending on where it is located. Therefore, this H2 can be written as H1 e to the power of j some theta, where theta is more or less uniformly distributed, because there is a path difference. The path difference leads to a phase difference, because the wavelengths we are looking at is we are looking at like 900 megahertz or something like that. Therefore, as long as d is close to lambda by 2, that is a few centimeters, right, at 900 megahertz, in that case, there is always a phase difference between the received signals. That's how antenna, in antenna design, that's how you construct different radiation patterns, right, using an array of antennas. Have you studied that? You have not had a course in antennas? Okay, fine. Okay, so but that's not quite necessary for us. As long as you adopt a model, that's good enough for us. But you need to understand the physics involved also. Okay, it's good to know how we develop these models. Okay, for the time being, H1, H2 up till Hn are statistically independent random variables. I mean, we sort of deviated completely from the underlying physics, propagation physics. Okay, we just deal with random variables here because we adopt a model, and this model is a good, reasonably good model. Okay, you may ask, what happens if I put multiple antennas at the transmitter side also? Okay, the same type of model can be extended. The signal, if I put another antenna which is not lambda by 2 apart, but sort of 10 lambda apart, large distance. Okay, there is a reason for that. Then this signal H1 will have a counterpart. If you call it H11, this will be H21. 2 corresponds to transmitter 2. Then these two can be modeled as, again, statistically independent random variables. Okay? But the distance between antennas at the base station should be a bit larger than this. Usually they are placed like 10 lambda apart. If you see the antennas on a base station, on a cell site, you see that they are placed a few meters apart. If you ever observed it. Okay? Of course, each antenna we are assuming an omnidirectional radiation pattern here. Okay, so the question here is, why are we considering a setup like this? Okay, why are we considering a setup like this? First, like I said, we will discuss a single transmitter, multiple antenna receiver, then we will generalize this. If it is a narrowband system, and if the channels have Rayleigh fading, having multiple receive antennas serves two purposes. Number one, it gives you what is called an array gain. What is an array gain? Having more receive antennas captures more energy. As a result, it produces more signal to noise ratio, higher signal to noise ratio. It's like having a large solar array. The larger it is, the more energy you capture. Somewhat similar to that. Okay, having a large array captures more and more energy. That makes sense, because it's very similar setting, right? There is a transmitter that is radiating, and we have an array that captures more and more energy. That's one benefit, right? So the signal to noise ratio can be improved. The second benefit is, if at all one of these channel gains takes a low value because of fading, the signal received on the second antenna need not go through a deep fade at the same time, because they are statistically independent channels. That's how we model them. If that is the case, you can always choose the best antenna, right? That's called antenna selection. You can always measure the energy and choose the one with the highest channel gain. That's called antenna selection. It's called selection diversity. Okay? What we are going to consider is a very general setup where we combine the received signals at the output of all these antennas using a filter with the complex weights W, and then it gives you a decision variable, let's say some zk, and you will demodulate your signal. And by combining, you not only coherently capture the energy contained in all NR channel paths, you also get diversity combining, which is of order NR, because you will get the sum of squares of channel gains benefit. We'll show that. That is the first benefit you can get. In this lecture, we're not going to specifically focus on this diversity combining gain. That will come about as a side product. Okay, we'll consider how this receiver array can be used to reject co-channel interference. Okay, that's what we'll focus on, and this diversity benefit will come about as a side result. Okay, so where is this co-channel interference generated? Well, if you reuse the frequencies in different cell sites because of scarcity of spectrum, then the signals arising from neighboring base stations will act as interferers. Okay? So, and if you use an antenna array with NR receive antennas, you can show that you can reject NR minus 1 dominant co-channel interferers completely. You can null them out using an antenna array. So, in other words, if I have 1, 2, 3, 4, let's say there is a desired signal, and let's say 3 dominant interferers coming from the neighboring base stations. Their strength may be a bit less than the desired signal because they are coming from a further distance. If I choose these weights properly and combine the output of these antennas, it's possible to place a null in the direction of those interferers. It's like forming a beam which is collecting energy from this transmitter and placing nulls in the direction of those interferers. That's one way of looking at this problem. That's not exactly how it works, but that's a way of understanding it. So you reject interference and you only capture the desired signal component.
So, but this set of weights will not be optimum for like maximum SNR, like selection combining and other like.
We will come up with a framework where this W, if you use a linear combiner, we'll come up with a framework where it is called an optimum combiner, and you will not find any other combiner better than this. So it will maximize the signal to noise plus interference ratio. It won't maximize signal to noise ratio, rather it will maximize the signal to noise plus interference ratio at the output of the combiner. Therefore, if the interference is present, it will reject the interference. If interference is absent, it will maximize the signal to noise ratio. It will do both jobs simultaneously. Okay? So, this framework enables one to reuse frequencies more aggressively. Right? When the spectrum is scarce, usually what happens is that people construct cells. These bubbles represent cell sites, use frequency F1, and if you don't want to reuse the frequency in the neighboring cell because it creates interference, then you have to use another carrier F2. Right? These are carrier frequencies. F3, F4, F5, F6, F7. And then you can reuse them later on, F1 here, somewhere here. Okay? So you develop these clusters, right? And you can have another cluster with the same structure repeating here, and F1 is somewhere here, and the distance between the first dominant interferer will be coming from a large distance, therefore the strength of the signal is low. Right? That is one way of designing cell sites. Okay? In the early systems, that's how GSM systems were designed. Okay? This carrier is not reused in the adjacent cell site. But on the other hand, if you reuse all the frequencies in all the cells, then you can increase the capacity in a significant way, because in the previous framework you need a lot more bandwidth, right? Now you can reuse them very aggressively in all the cell sites and use a technique of this kind to reject co-channel interference. So the overall spectrum utilization will increase, right? Okay, that's one benefit that you could possibly get from this. Then you may argue that, if you are close to the base station, anyway the interference levels are low, although there are a lot of interferers contributing, and you can live with it. Right? For data, for systems that that use data transmission, not voice, a signal to noise plus interference ratio of even 0 dB is acceptable sometimes, because it's a if it's a broadband system, you'll just use more bandwidth to get a given data rate. Sometimes a low signal to noise plus interference ratio is also acceptable. In such cases, you may want to reuse the frequencies very aggressively, okay, and the signal to noise plus interference ratio will naturally decrease because of more interference, and you need to do something about it, like introduce antenna arrays to reject co-channel interference. Okay, that's one way of improving the system performance. Okay, then the other application is, why not introduce multiple antennas at the transmitter? Why not introduce multiple antennas at the transmitter and use a linear combiner when the signal from this antenna is being detected? The rest of the data streams are treated as interferers. They're coming from the same source, but it doesn't matter for this linear combiner, right? They all act as interferers, and you can reject interference using this linear combiner and detect the data stream 1 reliably. Similarly, you can detect data stream transmitted from second antenna by treating everything else as interferers. So you can have a set of parallel receivers to detect all the data streams 1 to whatever the number of transmitters, and that is one way of increasing the data rate. And this technique is called spatial multiplexing. This technique is called for this to work, you need to have a very rich scattering channel where the channel obeys this IID property. That is, all the channel gains, right, between any pair of links has to be statistically independent. So you need a very rich scattering channel so that you can reliably distinguish these signals. In other words, if you are close to the base station and if you have line of sight, it's very, very hard to separate these signals. Okay? It looks as if all these antennas are coming from the same source. So it's hard to distinguish, separate. Okay? On the other hand, if there is a rich scattering channel, if all the channel gains are statistically independent, it's much easier to separate these signals. So in some ways, the multipath channel is sort of helping us to increase the data rate. Right? Some ways, the fading is good because it is helping us, or rather, we exploit the multipath channel to our advantage and increase the data rate of the system. So that's other way of looking at it. Okay. So what we will now do is we will develop the so-called MMSE receiver that will do interference rejection, right? And you can use it for the interference could be coming from an external base station, or it could be coming from same base station. It doesn't really matter from the receiver point of view. So let's develop such a receiver. Okay, so we'll begin with a system model. The received signal received at a given receiver can be written as okay. So what is this model? Well, we talked about a receiver with NR receive antennas, right? is H? First, what is YK? YK is the signals received from various Y1K, Y2K, YNR, comma K. So, I receive a signal on the first antenna Y1K and the signal received from second antenna, I stack them in a vector format. This is a vector of length NR. It's a column vector. Okay? And H. H is channel gain on the first antenna. Okay? And what is GM? This is the mth interferer. It could be coming from the same base station or from an external base. It doesn't really matter. This is the mth, the channel gain associated with mth interferer. So that would be and the modulation alphabet XM is the mth, XM comma K is the mth interferer, and MK is additive white Gaussian noise captured from all receivers. Okay, so if you look at any one signal Y1K, let's write it more explicitly.
So this number M,
Huh?
capital M, number capital M, that depends on
M is 1 till up till some number capital M. There are M interferers.
so this interference is dependent on the
Number of interferers. This is the vector of mth interferer. There are capital M interferers.
yeah, the capital M number.
We'll just leave it as some number for the time being. Right? It could be any number, 1, 2, 3, any number. Okay, we'll leave it quite general. Okay, later on we will derive the relationship between capital M and NR. Okay, we'll figure those things out. Right now it is just M. Okay, so let's write the signal model explicitly for Y1K so that you will understand what's really going on. So take the first antenna and see what you receive from the first antenna. What do you receive on the first antenna? H1 is the channel gain observed on the first antenna, and XK is the symbol that you transmitted from, it's called intended symbol. Okay, that is what you want to detect. Okay, that could be from your own, that is the first antenna of your own base station, or it could be a base station with a single antenna. Okay, that is the intended symbol. And you have GM1 XMK M equal to 1 to M. There are M interferers collected on the first antenna with a gain G M1 plus additive white Gaussian noise NK1. This is the model for the received signal collected on the first receive antenna. And if I generalize this for the Lth receive antenna, this will be HL, right? Where L takes values from 1, 2 up till NR, and I take all these elements Y1K, Y2K, YNRK and write it in this particular form in a very compact vector notation. Okay, first we wrote the vector model and then we wrote the scalar model here. Right, you can do the other. Do you understand this model? It's very important to understand this model. If you don't understand this, it's hard to proceed. Basically, we're talking about receiving a signal and M interferers superimposed and thermal noise and different antennas. What changes? The channel gains change, and they're all independent random variables in this particular case. And we're not going to consider path loss shadowing and all those things. They're not. We don't have to include them right now. If you want, you can include them on these channel gains, right? So
this X M comma K, what is the meaning? M comma?
Okay. K denotes the discrete time index. K denotes.
But I'm saying this XK will be the
time index. Okay. In fact, in this whole formulation, I can drop K because for convenience, you can drop K. Okay. M, then it becomes XM, right? XM is there are M interfering sources, each employing its own data. XM is a set of, it's a data stream. M varies from 1 to M. There are M interferers that are received at this receiver.
But aren't those sources coherent? Isn't the same symbol being sent by all of them?
No. If the same symbol is sent, then there is no advantage, right? You have to then capture that and then combine it with the symbol. See, the point here is each transmitter sends a different data. Then you can increase the data rate. If you send the same symbol, I guess there won't be much benefit, right? If you send the same symbol from transmitters that are located far apart, then you can combine them, those paths, then you will get some benefit. But we are not interested in that sort of benefit. That's very limited in nature. We are trying to increase the data rate of the system. If there are M transmitters co-located, and if they send M different data streams, what is the increase in the data rate? Theoretically M-fold. And capacity increase is theoretically M-fold. And if you can get M-fold increase in the highest NR limit, then it's a miracle, right? I mean, we have from the same transmitter we are sending just by adding antennas, you are increasing the bandwidth efficiency linearly with the number of antennas. So these antennas create bandwidth. It's a way of artificially creating bandwidth because you are simply linearly increasing the data rate with the number of antennas. So it's like a machine that creates a bandwidth. It creates bandwidth, a virtual way of creating the bandwidth. And bandwidth is very scarce. I mean, the spectrum is scarce. So any technique that creates an additional bandwidth is highly appreciated. Okay? So that's why these sort of techniques are very, very popular. Okay, they are employed in practical systems also. But of course, there are a lot of limitations on how to place these antennas, whether rich scattering exists or not. If there is no rich scattering, what you do? I mean, there are a lot of other things, but let's look at this simple framework for the time being. And good thing about this is that there is no feedback from receiver to transmitter. It's all open loop. That is, you transmit, you receive, and you separate the signals. And if at all you want to feedback something, you probably feedback that what is the post-processing SINR at the output of the receiver. That the transmitter needs so that it can assign the appropriate modulation coding on that antenna or for the data stream, so that you can get so much capacity. That's the type of feedback you need. Other than that, we don't need to feedback all these channels back to the transmitter, at least in this set. Okay, so it's sort of fairly simple system. Okay, so I'll erase this. I'll keep this picture and we'll derive the expression for W, and we'll give you an expression for the signal to noise ratio at the output of the detector, and then we'll go on and derive the conditions necessary. We'll derive the necessary conditions so that signal separation is feasible, and what is the relationship between M and NR and so on and so forth. How many signals you can simultaneously transmit so that you can separate them at the receiver using this linear combiner. Okay. So let's erase this. So keep in mind that these are all vectors. Okay. So now I'll write this decision variable zk as w multiplied by yk. You know, like I said, you can drop k because k plays no role in the setup because we're going to consider as if we transferred one symbol. Okay? But k simply denotes the time index. But let's keep it for the sake of general. So this w has a dimension 1 by nr and yk is nr by 1. So what is it really doing? We're taking w1 y1k plus w2 y2k and so on w nr ynr k. That's what we are doing. That is equal to summation wi yik. I equal to 1 to nr. That can be equivalently written as in vector form w into yk. That is the combiner we are talking about. Okay? So if I want to expand this picture, y1k multiplied with a complex weight w1 y2k okay, this is equivalent to this. So now our job is to figure out these weights W when you have a system model of this kind. Okay? You will show that, when this interference is absent, these W's will boil down to what is called a maximal ratio combiner. I don't know if you heard that. Naturally boils down to maximal ratio combiner, MRC. When this is present, we'll call this interference rejection combiner. That's the name we use. Interference rejection combiner. And we don't have to do much. It automatically tunes itself the weights such that when this is absent, it becomes maximal ratio combiner. When this is present, it becomes an interference rejection combiner. Okay? But what we will do here is that we will use the MMSE framework and we will derive an MMSE receiver that will act as an interference rejection combiner or diversity combiner naturally. Okay? It will adapt itself. So we are going to use the MMSE receiver framework which we used yesterday or in the previous two lectures for mitigating the intersymbol interference. Remember, we used an MMSE receiver to mitigate intersymbol interference. Here, we use the MMSE receiver to mitigate the co-channel interference. Why I call it co-channel? Because these signals are operating in the same band. Okay, they are lying in the same band. So, well, after all, they are interferences, right? They are interference, right? Whether it is co-channel or it is intersymbol, it doesn't matter. It's just an interference. So you will show that if they can be mitigated. However, to mitigate intersymbol interference, we didn't need extra antennas. Remember? But here, you need these extra antennas. Without that, it's hard to separate the signals. Where, to mitigate the intersymbol interference, we used different signals collected in different time snaps or in different frequencies and collected them and filtered them to mitigate ISI. So you had multiple copies of the signal either in frequency or time. So those are the copies you had available. Here you need multiple copies of the signal and interference in space. If you take multiple copies in time, they are highly correlated, nothing happens. Because you get the same signal, same interference, they are going to overlap. Okay? Because nothing really changes here. So you need multiple copies of signal and interference in space. Why is that? Something is changing in space, right? The channels are statistically independent. We exploit that property to knock out interference. Okay, so let's go through this receiver, and this receiver doesn't talk about how it functions. This receiver that we are going to derive simply gives you an expression for the receiver. It doesn't teach you exactly how interference is rejected. Okay, that we'll have to figure out by analyzing the performance of the receiver. Okay, so this Zk is W multiplied by Yk. And as I said before, after filtering, you should end up with what? Your desired signal xk plus some error ek. That's the job, right? After filtering, you should get your original constellation back with some error. Alternatively, ek is zk minus xk. To obtain these filter coefficients, we will minimize this error, minimize expected value of ek absolute value square, choose a filter W such that it minimizes this matrix.
But this xk must be a vector, right?
Okay, so it is, so we should write it as this dagger conjugate transpose. Okay, good. So that's how we should.
When you multiply w with yk, you will get a.
Oh, actually, this is a scalar. Actually, you can write it as like this or.
But in order to increase the bit rate, this xk must be a vector, right? That's why we are using multiple antennas.
Okay. See what's going on. Yk is a vector valued observation. W is the filter acting on it, and we have combined them. Okay. Zk is a scalar. Zk is equal to xk, a scalar, plus ek, a scalar. Okay. And at the output of the combiner, you want to minimize the variance of ek. Okay. You want to minimize the variance of ek. Therefore, you want to minimize expected value of ek square. Okay, so which is a scalar. Does it make sense? You combine first, bring it down to a scalar model, and then minimize the variance and the output of ek. Okay?
Oh, I didn't understand what's going on.
Okay. We're doing something similar to what we did in the previous lecture, but this is a different setup. You had a vector valued input. Okay? You apply certain weights on them. And then you combine them. This is the receiver we are going to consider. We have imposed ourselves this receiver on us. This is how we are going to detect the symbols. So, when you combine them, what do you get? From vector valued input to scalar. So, this is called SIMO, single input, multiple output. Okay? These are. Okay? This is called a SIMO system, single input, multiple output. So, Zk is scalar as if you have transmitted a constellation and it is corrupted by some filtered noise. Okay? Now, you want to design these weights W. You choose this W such that the variance at the power contained Ek is minimized. Okay?
So how the bit rate has increased?
This receiver doesn't talk about all those things. That we will show. If this receiver is able to separate all the signals and deliver a post-processing SINR at the output of the receiver, that is 1 divided by the mean square error is high enough, then we will figure out whether the bit rate has increased or not. Okay? This is the receiver, that the job of this receiver is to separate signals. That's all. It doesn't care what is the setup, whether these transmitters signals are either co-located or they're far apart. That's not. No, the receiver doesn't care. Okay. We'll show how it is increased. Let's proceed. So now, in some yeah.
Ek is a scalar, so it will be simply conjugate, Ek conjugate into Ek.
Yeah, that is Ek absolute value square. So instead of going like we said, you can differentiate this with respect to W and plug in the expression for EK. You can go through all that. Instead of that, I'll use the orthogonality principle that directly gives you the desired result. Okay, that you have to go through any book on estimation. Okay. Using the orthogonality principle, expected value of, well, it says that the error is orthogonal to the input. Error is EK, input is YK, it is orthogonal, so you have to put a conjugate transpose. If you're dealing with vectors, you have to put conjugate transpose. If it is scalars, you put a just a star. That is equal to 0. That's what the orthogonality principle states. So now substitute for EK. And substitute for ZK, which is okay. I'll proceed here. Move this expectation inside. Do you agree with this? Okay. And W can be written as this. We'll call it RXY, and we'll call this RYY. So W will be RXY multiplied by RY by inverse. Okay, let's expand what RYY is. We need to know what it is. Let's see what YK is. YK is H times XK plus, we'll call this entire noise plus interference NK delta. Okay? Just to make things simple. Okay? This would be H Hermitian, expected value of XK Hermitian, sigma x square. We assume XK, some assumptions here. And in fact, you can choose the variance of xk and xm to be unity without loss of generality. So we'll assume sigma x k square is equal to sigma xm square equal to 1. And xk and xm are also statistically independent of each other. Or IAD, they are also independent of each other. That is, we are sending different data on different. When you say interference, there are, by definition, it means different data. Otherwise, you don't call it interference. We'll finish that. And the expected value of xk Hermitian is sigma x square. That will be unity. Plus now,
we are using that model in YK.
Yeah, hxk plus n tilde k. Okay, this is n tilde k. Just note that n tilde k is. We'll explain it somewhere here. I'm just running out of space. Okay, we'll write it here. So these are the assumption on xk. So RYY is H Hermitian sigma x square plus, and we said n tilde is, let's expand what n tilde is, n tilde k okay, and by the way nk is AWGN. Okay, nk is AWGN by default. Additive white Gaussian noise, standard AWGN. Okay, so you tell me, what do you see here? Well, the cross terms should go to 0, right? Because n tilde k, all the terms in n tilde k are statistically, xm and nk are statistically independent of xk, so cross term will go away, and you will end up with expected value of nk, n tilde k, n tilde k Hermitian, and that I would call R n tilde. Okay, and R n tilde is equal to expected value of n tilde k Hermitian. Okay, let's evaluate what it is. That is equal to expected value of this whole thing I'll write the answer directly because I don't want to write a long expression here. N tilde k multiplied by n tilde k Hermitian and take the expectation. Okay? Just see. You will get expected value of GM Hermitian sigma m square sigma xm square. Do you agree with that? This multiplied with conjugate of this. This is a vector, term by term. You get GM Hermitian xm square plus expected value of nk Hermitian n naught into identity, and all the cross terms are 0 because xm are IID and they are independent of nk. Would that be okay? So now we know R by Y. Okay? So we know R by Y and we need to know RXY. RXY is expected value of xk and yk Hermitian. Yk is h times xk, put a Hermitian on both. I didn't take this other side because this is a scalar. When I did Hermitian, this is a vector. And nk tilde Hermitian, and that should be equal to sigma x square multiplied by h Hermitian. Okay?
Is xk also?
What is it?
Is xk also vector?
Xk is a scalar. And xmk is also a scalar. That's why things are simpler. If it's a vector, then it will get a little complicated. Okay, so now we have an expression for W, which is R xy RYY inverse, that is equal to RXY is sigma x square h Hermitian and h Hermitian plus RNN tilde, which is I don't know if it is visible on the screen. I think it is.
There must be another sigma x square after HL.
What is that? There is a sigma x square here. In a moment we'll make all sigma x squares 1. Okay, that makes things simpler. If it is not 1, you can always absorb it as part of the channel. You can absorb, say, square root of sigma x square into the channel. Okay, so it's not really. So you can always take sigma x square equal to sigma xm square is equal to 1. Okay. Now,
What is
huh? Identity. What is the dimension of this matrix? Well, nr by nr. Okay. And this is a nr by 1 vector. And this is 1 by nr. Total you have nr by nr. And you sum up capital M nr by nr matrices. Okay. So this I would call a direct form of MMSE. Okay, this is called if you just work out the MMSE, this is what you get. You can implement the receiver. So what is that you need to implement this receiver? Can you tell me? You need the knowledge of H. You have to estimate it. And you need the knowledge of Rn tilde and Rn tilde. Either you estimate it directly, the covariance of interference by some means, or if you know the channel keys of all the interferers, individual interferers, somehow if you can estimate it, you can explicitly construct this quantity. Either you estimate this quantity directly without knowing the individual channel states of interferers, or if you can estimate the interference channel states, which are GMs, then you can explicitly construct those. So there are two ways of estimating. So if you send a pilot sequence, known data sequence, using the pilot, you can first estimate the H. That you can estimate the second order statistics, the covariance of interference. So if you have a pilot sequence, you can do this. Okay. So let's not worry about how to estimate these parameters. That's a separate exercise. We'll just derive the receiver structure. Okay. There is what is called an indirect form of MMSE. Okay. And I will not show you the derivation, but I will write you the expression and I will give you a hint on how to get it. Okay. From here, you can reach here. How do you do that? You have to use what is called matrix inversion lemma. Okay, what is this matrix inversion formula? A plus BCD whole inverse is equal to A inverse
Okay. X square is a scalar.
Yeah, you can put it as 1 here if you want, okay? So, from here to here, you have to use this formula. Okay, I won't show you all the detailed steps involved. Okay? But we will use this expression for implementation rather than this. There is a reason for that. Okay. The reason is that this is a scalar. Okay. The reason is that this is a scalar, and this type of receiver is much more intuitive. Okay. To explain. Here there is a vector and there is a matrix inverse. Here there is a vector and there is also a matrix inverse. But this matrix only contains Rn and tilde, which you can estimate. Whereas this contains both Rn and tilde and covariance of the desired signal. Okay. So this is called indirect form of MMSE. And this is a scalar, and it has no role in dictating the performance of the receiver because it's a scaling constant, right? This whole thing is a scalar. So therefore 1 plus something is a scalar. Okay, before we proceed further, first I will derive an expression for the mean square error. The mean square error for this receiver can be shown to be, I won't go through the details, 1 plus H admission Rn tilde inverse H whole inverse. Okay, that is the mean square error that you can show it. And the signal to noise ratio at the output of the MMSE receiver unbiased, and throughout we assume sigma x square is equal to 1, and that would be and if you remove the bias, the way I explained it in the previous lecture, because you just remove one, right, from that. You know, you don't have to go through all this. You can simply look at this expression and see what's really going on. Okay? From this, you can explain many things directly. Okay? That we'll see. Okay. W is equal to 1 plus this is a matrix, this is a vector, and the whole filter is 1 by NR. Right? That is consistent with our definition of W. And what is this? Well, this is something related to the bias, and you can simply ignore this term. So you can multiply W with 1 plus H admission Rn inverse H, so to get rid of this term. Okay? Or you can pass this whole thing so you can simply call WH as your new channel. Okay? Which is a scalar. Then you are ready to demodulate your symbols. Right? That's all. So you don't have to worry about bias or anything. WH is your new channel, which is a scalar. So that is the biased. Okay? So alternatively, if I drop this from the filter expression, right, you can safely drop it because it's a scalar, right? So a scalar doesn't change anything. So my new MMSE filter would be only this. Okay? So So I can take W from tilde as H Hermitian Rn tilde inverse. It has an interpretation. This is called a noise whitening filter and this is called a match filter. Okay? And this is a match filter, spatial match filter. This match filter is a little different from the one we encountered yesterday, where this match filter is a spatial match filter. Okay? If there is no interference in the system, what would be our MMSE receiver? W tilde can be written as H Hermitian. What would this be? 1 over N naught? 1 over N naught. Identity goes away. So you can drop 1 over N naught. Right? From a filter, scaling can be removed. And what is your optimum solution? H Hermitian. What is that? And Zk for match filter this I will call it match filter is equal to H1 conjugate Y1 K plus H2 conjugate Y2 K plus HNR conjugate YNR K. This is also called, what is it called? Maximum ratio combiner. Or MRC. See, we started with MMSE and we ended up with an MRC. Sort of we established the equivalent relationship. Why is it called maximum ratio combiner? Well, it maximizes the signal to noise ratio at the output of the receiver. Okay? And what did we solve in this case? We minimize the mean square error, and if you remove the bias, MMSE receiver also maximizes the signal to noise ratio at the output of the receiver. Signal to noise plus interference ratio at the output of the receiver. MMSE receiver with bias removal is equivalent to maximizing the signal to noise plus interference ratio. Okay, this is the special case. Okay, we have handled one problem. Now let's look at what really happens in the presence of interference. We call this filter a noise whitening filter. Why? We'll apply it and see why it is called a noise whitening. So this, I'll put tilde here. H Hermitian Rn and tilde H xk plus nk tilde. Okay? So expand the terms. Okay? So this is my signal amplitude. This is my noise amplitude. They are all scalars. This is 1 by NR. This is NR by 1. This is 1 by 1. And this is 1 by 1. They are all scalars. Okay, this is what we are going to pass to our demodulator. Everything should be scalar. Okay? Now let us calculate the signal to noise ratio on this. Yeah. Yeah, let's finish this and okay. The signal to noise ratio on this would be, what time is it? It's 12, 20, okay, we exceeded. This would be done here almost. The signal power is can you tell me what is the noise power on this? The variance of this. H Hermitian Rn tilde inverse and expect the value of n tilde k into n tilde k Hermitian, that would be Rnn. And again you will get Rn tilde inverse H because you will take Hermitian of it, and this cancels this, you will get H Hermitian Rn inverse H, and this would be square because amplitude square is a power, and you will get H Hermitian Rn inverse H. So what this does is that it takes noise which is colored in spatial dimension, it has a covariance, and it makes it a white noise. Okay? We'll show that later. It makes it white noise. So at the output of the MMSE receiver, the noise plus interference signal becomes spatially white. We'll show in the next lecture what it means. Okay, let's stop here. So this kind of receiver is easy to implement in MATLAB. All you have to do is generate this, develop this, apply and detect. 3 steps. Generate this, which you have to generate this model. Apply this filter, H Hermitian Rn inverse. Rn is defined. Apply and detect. Then you will see whether the interference is rejected or not. Okay, so you can see it for yourself. It's only like 5 lines of code.